Okay, so we're looking at graphs today. So what we want to know about a graph, particularly to differentiation, is all the aspects of it that we could be asked. So the questions in this particular vein of questioning in the test will be usually little snippets. You won't have to do the big thing, but we're going to drive towards the big thing because it's important for you to know the whole process. So we're going to look particularly at polynomials, but whatever particular rules apply to any graph. All right, so let's have a look to start off with. If we have a polynomial, I'm going to go for a cubic, e.g. y equals x cubed plus 4x squared plus 2x minus 8. I don't know. Let's hope this one works. If it doesn't work, well, we'll discover some other things about it. But basically what we're doing here is, to start off with, we need to understand what this graph looks like. What kind of graph is it? Okay, what does cubic look like? Right, a wiggle. On the whole, it's a wiggle, right? Starting at one place, going to another place. We know so much about this from graphs last year. We know it's a positive cubic, therefore it starts down here and it goes wiggle, wiggle, wiggle like this. What we don't know and haven't been given is that factorised form of when it would go through the axes or all of those sort of things. We could find that. All we have to do is put this into our calculator. Our graphics calculator will tell us solutions for this. That will help us to find those x-intercepts. That's not calculus. So we're not going to be asked to do that. What we are going to be asked to do is, about last year we told you that you couldn't really find where it wiggled up and where it wiggled down. It didn't really matter. Just draw the graph, make sure you hit the y-axis and the x-axis in the applicable places. But we're now growing it up a whole level, and it does matter. We can find out where those points are by using calculus. You learnt the basics of this last year in Year 12, but there's so much more to learn now in Year 13. So because we've got all our other functions that we can actually use. So we could be doing this to an e of x graph, but interestingly boring. So it's more likely that you get something that was a trig graph or a trig combined with something else graph, like an x squared sine x graph. And what does that look like and how does it behave? So it's the behaviour of the graph we're actually looking at. So the rules say that if we differentiate it, and if it's equal to, if it is greater than 0. So for any values of x that you put into the differential where the result is greater than 0, the graph will be, so what does f dash of x give us? It's the gradient function. When is the gradient greater than 0, the graph will be, and our word for that positive is? Increasing. All right, this will be an increasing graph. Yes, it will have a positive gradient, it will be increasing. Okay, so that implies a positive gradient, which gives us an increasing function at that point. All right. At some point in time, because it's a cubic, it's going to slow down, it's increasing, and it's going to come to a maximum or a minimum or a turning point. All right. So f dash of x equal to 0 will indicate a 0 gradient, which indicates a turning point. All right. If our f dash of x is less than 0, then we have negative gradient and a decreasing function. So, should our graph, and I have no idea what this graph looks like, perhaps it looks like this. All right? What we need to be able to do is identify where these 2 points here are and break it up into those zones. So we've got at this point and at this point, f dash of x is equal to 0. The gradient is 0. In between those 2 points, from here to here, f dash of x will be what? Less than 0 because it's decreasing. And from here to here, and here to here, we've got greater than 0. Right? So because those things are how it works, we need to be able to find these 2 points. The easiest way to do this is just using our graphics calculator and putting this into the polynomial solver, degree 3, because probably what would come out of that, I have no idea whether it's true or not, will be a whole lot of decimal values. They won't be nice factorised ones most of the time. So that's not part of the test. So with our turning point, we've got 3 things that can happen. As you said, we've got the case where the turning point's at the top. That is a maximum value. There's no values above that. We've got this case, which is a minimum. And we've got this case, or it could look like that, which is a point of inflection. Actually, that's not quite. Need to draw those a bit better. It has to go through a gradient of 0 for it to be a turning point. All right. So how would we find out what is what? Well, at the moment, and I know you know the next step of this, but today we're going to look at testing points. So what we could do is where we've got f dashed of x equal to 0, let's say it happened at f dashed of a, we can pick points just below a and just above a, all right? We can test them in f dashed of x and it will tell us what's going on. So if we put a just below a in here and we get a positive, we're going to get a 0 here because we're testing a point that is a maximum or a minimum or something. And if we put just above a in here and we get a positive, all right, we can see that that graph is going to be, that point will be a turning point. All right, so we can understand what's happening in a graph. Now, the only problem with doing this is that you must make sure your A minus and A plus, or your points just outside of A, are not on the other side of another turning point. All right, so the case being if you choose this is A and you choose this value here as A minus and this value here as A plus, I've got that story, right? But that's not the graph. So you must make sure that A plus is not after another turning point. It needs to be here. All right, so this needs to be A plus. And therefore we would have got a positive, a negative, a 0 and a negative to give us the answer that at that point A we had a maximum. All right, that's what we're going to do today.